So it's a great pleasure to welcome all of you to the next Q+ Hangout. And today's speaker is Joe Fitzsimons, who's currently at the National University of Singapore and previously was at Waterloo and also held a junior research fellowship at Oxford. And he's going to talk about universal blind quantum computation, and we're very thankful that he's willing to do so. He's joining from Singapore today, so it's the furthest east speaking participant so far in the Q+. And thanks very much, Joe. Please go ahead.
Okay, well, thanks very much. Hopefully everyone can hear me okay. Okay, so today I want to talk about blind quantum computation, which I guess Elham knows all about already, so I'm not quite sure what she's expecting to hear. But hopefully I can say something interesting for the rest of you. So the basic idea is I want to talk about kind of a cryptographic problem where you want to convince yourself that a remote quantum computer is doing your bidding, basically. You want to be able to delegate some computation to some remote server and convince yourself that the results you get back are correct and that the remote computer hasn't interfered in any way with your privacy. So I guess I'm going to switch to the slides now and start the talk properly. Okay, so hopefully you all have the slides up now. Okay, so basically the problem I want to talk about is this. You have some person, Alice, who has limited computational power, but wants to be able to use a quantum computer. And there's another person, Bob, we'll call him, who has a quantum computer, a universal quantum computer, and is willing to help Alice. But the only problem is Alice doesn't trust Bob, and Bob won't give Alice his quantum computer. So what can we do about this? Well, the basic idea is that we want to encode the computation in some way such that Alice's input, the output of her computation, and the computation she's performing all remain hidden from Bob. So this means we're going to have to encrypt it in some way. Okay, so this is just a slide taken from a table in our original paper that summarizes what was known about this circa 2009. So there were some previous papers that demonstrated the ability to hide certain functions with varying levels of security. And the basic idea of our protocol is to be able to hide a universal computation in such a way that the blindness is absolutely guaranteed, so that there is no possibility for Bob to learn anything about your computation. We also want to make sure that Bob can't interfere with the computation. And this isn't something that had previously been done before, although since this time there have been a number of variations on our scheme. I guess Tomoyuki has a couple. Also, there is a paper by Dariush Aronov, Michael Benor, and Ilad Iban on doing something similar with fixed-sized quantum computers for Alice. So Alice gets a fixed-sized quantum computer in their scheme, and she interacts with some remote quantum computer. So in our setup, things are a little bit different. Alice doesn't actually have to have any significant quantum power at all. We assume she can prepare individual qubits in one of a set of states, and that she can do classical polynomial time computation. Now, it's actually possible to get rid of this requirement for Alice to prepare quantum states entirely if we're prepared to have two non-communicating remote servers. But I'll maybe get to that a bit later. So our approach to this problem is fairly simple. It comes from a model of quantum computation called measurement-based quantum computation. And in this model, you create some resource state. Usually they're called cluster states or graph states. And they're called graph states because you can this resource state corresponds to a mathematical graph, so some set of vertices and edges. So you can probably see down at the bottom here there's a graph drawn in for the resource state. And what this would correspond to is preparing each vertex. Each vertex corresponds to a qubit, and the qubit's prepared in the plus state. And each of the edges in the graph correspond to applying a control Z gate between the corresponding qubits. And then what happens is each qubit is measured in turn with subsequent measurements depending on the outcome of previous ones. So when you measure a qubit, you may need to take the result of that measurement into account to calculate the next angle for the next measurement. So our basic idea is to associate Alice with this classical control computer, and to associate Bob with the preparation of the resource state and the actual implementation of the measurements. So, just to show you what this actually looks like, if we write out this setup, a graph, so you'll see a graph up at the top here, and this is the corresponding circuit. So if you leave out the measurements, you prepare all the qubits in the plus state, then you apply control Zs between them according to the graph, and then you have some order to apply the measurements in. So you apply the first measurement, get some measurement result M1, then you do the second measurement, get a result M2, and so on. Now, in the original paper on measurement-based computation, and many of the subsequent ones, the measurements that were required were restricted to either the XY plane, so the equatorial plane of the qubit, or the Z-axis. So I've just called, the XY plane ones, I've parameterized them here by phi1, phi2, phi3, and I've thrown in some Z basis measurements here, which I've just marked as Z. So this circuit here corresponds to some measurement-based computation. And basically what we do is we rewrite the circuit in a slightly different way. So each of these measurements can be expanded out. So the XY plane measurements can be written as a Z rotation followed by a Hadamard and then a measurement in along the Z axis, or in the Z basis. And the Z basis measurements are just a straight up measurement in the Z basis. Okay, so you can expand this further. So each of these rotations here by the angle phi1. So if we want to implement this, we can actually split this into two parts. So we can have it phi1 minus theta 1 and a rotation by theta 1 as well, for example. So when you multiply, these two rotations commute with the control Z operators, so the total rotation applied is exactly the same as on the previous slide here. So these two circuits are identical. And we can go a step further and add in some more Z rotation. So here we're doing phase flips. And this is just, we're writing it, so we have a phase flip times some random number that's either 0 or 1. And we've thrown that in. And this flips the output measurement. The output of the measurement conditioned on whether OR is 0 or 1. So actually the output you get of this circuit is now XORed with this string, R1, R2, R3, R5, and R7. Also, the thing for the non-XY basis measurements is that the measurement itself commutes with all of the control Zs. So, for example, in the fourth line here, we're able to pull the measurement all the way through and measure the plus state. Now, we already know in advance what that is, so we don't actually need to do that measurement. but we can prepare a qubit that corresponds to the possible outcomes of it. So the basic idea is to associate Alice with the preparation part of the circuit, so this preparing a plus state and applying these rotations to it, and then have Bob do all of the entangling operations. Then he's going to do some measurements in the XY plane, and then Alice will do the decoding of the measurement results. So if we get out some measurement result from Bob, Alice is going to have to compute the XOR of it with her randomly chosen numbers, or 1 or 2, and so on. So this is the main. This is the final circuit. So Alice is preparing these qubits. Either here they're qubits in the XY plane, or for the ones that are to be Z measured, they're randomly chosen in the as Z basis eigenstates, or Z eigenstates. So Alice prepares the qubits, Bob entangles them, does the measurements, and then Alice decodes the measurements by XORing them with her random choice of numbers. So basically, what's happening is we've two things going on. It can be viewed as a single qubit teleportation for all of the XY plane measurements. So we have some input state phi. We apply control Zs to the neighbors. We measure in the XY plane. And then we need to apply some correction operator here at the end. But this gives us a Hadamard gate followed by a Z rotation followed by a Hadamard gate on our input state. And what we've done is to have Alice prepare some input state that's rotated by theta. Now Bob is going to do the measurement in the basis that's been rotated. It's had theta added on to the actual angle of measurement, and then the measurement result is XORed with OR. So something I've done here is I've used theta prime to be the sum of theta plus OR times pi. And that's something I'm going to use later on because it makes showing the blindness easier. And then with Z-basis measurements, I've done something fairly simple as well. So if we have some input state psi, and we want to measure it, well, this is exactly the same as measuring a plus state that was at the, I kind of skipped a step here. So if we want to measure this state phi, it's the same as teleporting it in and then doing a Z-basis measurement, which is essentially the same as if we do the Z-basis measurement on the plus state and then apply a feed-forward correction from the preceding measurements. Equally, if we wanted to do a Z-basis measurement on a graph state, so the Z-basis measurement is here, we can do exactly the same thing. Okay, so that probably wasn't as clear as it could be, but the basic idea is that we have a way to hide XY plane measurements or Z measurements. I'll prove to you in a minute that this actually hides them. But I want to say something first about the resource state. Because our goal is to hide the computation being performed, we need a resource state that doesn't reveal information about what the computation is. So originally, when we came up with this scheme, we didn't realize that we could do these Z-basis measurements in a blind way. And so we made a scheme, we came up with a resource state that only required XY plane measurements to be universal. And so this is something we call the brickwork state. And this is kind of a depiction of the graph here. So you can see it's a regular graph that has a, so it has repeated kind of unit cells that are tiled to make the full graph. And each one of these unit cells can be used to implement a quantum logic gate, depending on how we choose our measurements for the qubits in that section. So we can apply local rotations through angles alpha, beta, gamma here, just by measuring the first 3 qubits in arbitrarily chosen bases and the last 2 in the x basis for each line. We can apply a Hadamard gate, pi/8 gate, or the identity. But we can also apply entangling gates. So here's an example of a control NOT gate. So given this set of gates, we're able to implement a universal quantum computation. We're able to implement a universal set of gates, and so we can implement any quantum computation if we're given a sufficiently large brickwork state. Okay, so to tell you how the protocol works, it goes as follows. Alice prepares individual qubits prepared in the XY plane. At the moment, I'm only going to consider XY plane measurements because in the original scheme, we didn't use any Z-basis measurements at all. So Alice prepares these qubits in the plus state, rotated by this angle theta. And this is going to be chosen uniformly randomly for each qubit that Alice sends to Bob. So Bob collects the qubits Alice sends to him and arranges them in a lattice. And then he applies control Z gates according to the brickwork state scheme. Then for every qubit that Alice has sent, so for every qubit x in column y, Bob is going to be sent an angle delta xy by Alice. And so Bob measures in this angle delta xy and sends the result of the measurement back to Alice. So that's going to be called MXY. So this is exactly the circuit that I showed you before, which is identical to a standard measurement-based computation, where you're just doing XY basis measurements. The nice thing about it, however, is that we can prove that Bob learns nothing other than the dimensions of the brickwork state, which, as it turns out, will correspond to the dimensions of the quantum circuit. Okay, so we want to prove that there's no information leaked. And to do that, we need to define a notion of blindness and what it actually means for the computation to be blind. So we're going to say a protocol is blind on a given input if it leaks at most Lx. So given an input x, if it leaks at most Lx, if the information that's obtained by Bob depends only on Lx. So Lx is just some function of the input x. And in our case, it's going to be really simple. Lx is just going to correspond to the circuit dimensions. Okay, so basically we want to show that there's no information leaked other than information that depends solely on the depth and width of the circuit, of the quantum circuit being performed. And indeed, these can only be upper bounds. It doesn't have to be exactly the circuit dimensions. So Bob obtains 3 pieces of information. He obtains the parameters specifying the brickwork state, because he gets some qubits and he needs to entangle them according to this brickwork state. So he has to be told the depth and width of the brickwork state. He also receives some qubits from Alice, and then he receives some classical information in the form of being told these angles delta in which to make the measurements. Okay, so first of all, the parameters of the brickwork state correspond to the dimensions of the circuit directly, basically because each one of these blocks Each one of these blocks here, U1, U3, U2, corresponds to a single gate. And so the depth of the circuit corresponds to the depth of the brickwork state corresponds directly to the depth of the circuit, the quantum circuit you want to perform. Although, of course, you can pad it out with the identity, so you only reveal an upper bound on the depth. And equally, each row here corresponds to a qubit, to a logical qubit. So the width of the brickwork state is revealing an upper bound on the number of qubits in your calculation, or logical qubits. Again, here you can pad it. So you can have some extra qubits that don't interact with the rest of the circuit. So again, you're only required to reveal an upper bound. But you necessarily do reveal that. And indeed, it's impossible not to reveal upper bounds on these numbers for any delegated quantum computation. So there's no scheme you can think of where Bob doesn't learn the maximum number of qubits his device can hold, or the maximum amount of time it took to implement the circuit. And you can think of this circuit depth, the depth of the brickwork state, as basically corresponding to the time it's going to take to run the algorithm. Okay, the second thing is the qubits that Alice receives from Bob. That Bob receives from Alice. So these are all prepared in this. Each one is prepared in some state. That's a superposition of 0 plus 1, and the relative phase of those is given by this angle theta prime plus OR. So theta prime I plus OR I for the ith qubit, where OR I is some secret value. Now, this is the only thing in the entire protocol, the only bit of information that Bob receives that depends on the specific value of OR I. Nothing else depends on OR I. So if we trace over OR I, then we get for every qubit we get the maximally mixed state. So Alice is just sending Bob. If he doesn't know the secret OR I, then what Bob receives is always the maximally mixed state. Now, if we are also doing z-basis measurements, which I didn't include in this protocol, but I'm going to talk about them later, so I may as well show that they're also blind here. Because you're sending either the 0 eigenstate or the 1 state with equal probability, again, if you sum over these, you get the maximally mixed state. So if Bob doesn't know ahead of time which one he's going to be sent, then he receives an identical state to if it had been an XY plane measurement. So the state of the quantum system is not determined in any way by the computation to be performed. It's always fixed as the maximally mixed state. So it's just a tensor product of single qubit maximally mixed states, unless OR is taken into account. But if you trace over Alice's secret, then you're getting the maximally mixed state here. Now, so this doesn't depend on any. This doesn't depend on the computation being performed, but also, even though I had written psi I as a function of theta prime I, here it turns out it's a constant function, so it doesn't depend on the value of theta I at all, or theta prime I should say, at all. So it only depends on correlation. So if OR I is unknown, then it depends in no way at all on theta prime. Which means that the only thing in the protocol now that depends on theta prime I is delta I. So delta I is the sum of the angle we actually want to implement for our measurement plus theta prime I. But since theta prime I was chosen uniformly at random, delta I doesn't depend on phi prime I at all. It's also uniformly random. So now the information Bob receives in the protocol is always uniformly randomly chosen from the set of possible angles and the set of possible qubit states. So he's getting a maximally mixed state of both the classical information and the quantum information. So the state Bob receives, the reduced density matrix for it, is entirely independent of the computation being performed. So the only thing that the protocol is leaking to Bob is an upper bound on the circuit dimensions. Okay. So I want to talk about extending this. So far I've tried to show that the only thing Bob learns is an upper bound on the circuit dimensions, and he doesn't learn about the computation being performed. But this is in no way a proof that Bob can't modify the computation. So we need something else. It's entirely possible for Bob to distort the result of the computation in such a way that Alice can't detect it. So we need to add in some extra structure on top to detect whether Bob interferes with the protocol to produce an incorrect output. So if Alice doesn't trust Bob to implement the result correctly, to implement the protocol correctly, then she can be sure that he won't learn any information, but she's not yet sure that her output is correct. If she's factoring, then there's no need for her to worry about this. She can just test the factors afterwards and determine whether or not they are indeed factors of the integer she was trying to factor, or the same with discrete logs or any problem that's in NP. So if the problem's in NP, she has an efficient means to test whether or not the result is correct at the end of the computation. So there's no need for an authentication mechanism. However, there are problems in quantum computing which are believed to be outside NP. So if we want to simulate a quantum system, for example, determining whether or not the outcome of our simulation is correct is not easy. We can't necessarily do it with a classical computer. The best thing we can think of is more or less to run another simulation of the same thing on a different computer and compare results. But these are open to interference if the computers themselves can't be trusted. So we want some mechanism whereby we can be sure Bob did not interfere with the computation, and therefore the result of the computation must be correct. And to do this, the basic ideas are very simple. We want to create some qubits which we're going to call traps. And the basic idea of these trap qubits is to detect whether or not Bob has interfered with the protocol. And the way they're going to do this is they're going to be individual qubits within the resource state which don't become entangled to the rest of the system. So when Bob makes a measurement on them, Alice already knows in advance what the correct measurement result should be. So if Bob gives an incorrect measurement result, Alice will know he cheated. Now, because there's only a finite number of traps, there's always some polynomial probability that Bob can guess a qubit that's not a trap. So he can just get lucky and guess a qubit, guess whether or not a qubit's part of the computation, change that qubit and only that qubit, and let the computation proceed. And then the probability of him getting away with this is going to correspond to the fraction of traps versus as a function of the total number of qubits in the brickwork state. So we want to amplify this because this is only going to give us some kind of polynomial security. So we want to make sure that we have something stronger, that we can make the probability of Bob cheating arbitrarily small without a huge explosion in the number of qubits we need to implement the protocol. And so the way we do this is we use error correction. and fault tolerance to ensure that unless an error occurs on at least S many sites, the output of the computation is correct. So we're just going to use a standard fault tolerance scheme with the promise that errors need to occur on at least S sites in order to cause a logical error. And because they have to occur on S sites, and those S sites have to all avoid the trap qubits, we're going to get an exponential suppression in the probability of Bob successfully cheating. Okay, so just before I start telling you about the resource state, which we use for this, I just want to review two quick rules from measurement-based computation for what happens when you measure a graph state. So if you measure a graph state in the Z basis, it turns out that you can rewrite this as another graph state. And the way you get there is you just remove the qubit you measured and all edges connected to it. Now, if you've got a measurement result 0, you get exactly this graph state. And if you get a measurement result 1, then you have a local Pauli Z operator applied to each of the neighboring qubits. But you can undo that with just local operations. There's no entanglement necessary. So it's locally equivalent to this, this new graph state that you get by just removing the qubit and its associated vertices. Similarly, if we measure in the Y basis, there's also a transformation rule. So if we measure the same qubit in the Y basis instead, this results in another graph state, but this time we get it by connecting any neighbors that were not previously connected with edges, and any that were previously connected we disconnect. So there's a little picture down here in the bottom to give you an idea of what that looks like. But basically, if we're removing this white qubit, we get this extra edges introduced between the neighboring qubits. Okay, so this brings me on to a new resource state that we can use. So originally we considered this brickwork state because we didn't think we could make Z-basis measurements. And that meant we needed to use our XY plane measurements to essentially cancel out entanglement in a careful way whenever we wanted gates not to be entangling. But it turns out there's a much easier way to do this because we can just do Z-basis measurements. So what we do is we take a complete graph. So this is the complete graph on 6 vertices. So complete graph just means we connect every vertex to every other vertex with an edge. Okay, so we start from this, and then we add an extra vertex in the middle of each edge to get this. Okay, the idea is that if we use something like this as our resource state, we can determine whether or not, well, we can make any graph state of the black vertices simply by measuring the qubits corresponding to the red vertices in the Z basis if we want to remove an edge. So if we want no edge between, say, this vertex and this vertex, we measure the red qubit, the qubit here in the Z basis. So the rule says then we remove that vertex and its associated edges. And if we want to introduce an edge, we instead measure it in the Y basis, because the rule for that is then going to say we complement its neighbors, so we add an edge between the two black vertices, and then we remove the red vertex and its edges. So from this we can get any graph we want of the black qubits. I'm sorry, of the black vertices. So we can have any 6-qubit graph state we want, simply by appropriately choosing whether or not we measure the qubits in the Z or the Y basis for the red qubits. And then we're free to measure the black qubits however we want. Okay, so the way authentication is going to work is fairly simple. The idea is to introduce trap qubits on one subgraph and do the computation on another subgraph. Now, actually, you'll notice that we don't really have one type of qubit. We've two types of qubits. We've got the qubits that correspond to a black vertex and the qubits that correspond to a red vertex. So actually, we're going to have two types of trap qubits because we need to be able to detect any malicious error or any environmental error on either the black or the red vertices. So actually, we'll have three subgraphs which will correspond to red trap qubits, black trap qubits, and the computational resource state. So we can get these by choosing some set of qubits. So if we just pick, if we partition the black qubits into three sets, three equal sets, randomly, then we can choose, we take the vertices that correspond to links between black qubits in different sets, and we set them to be Z eigenstates. So this is the same as measuring them in the Z basis. So this gives you three disconnected graphs that are all identical. Okay, and the black vertices in each graph are randomly chosen. So there's no correlation. I've only drawn them here for convenience to be located near each other, but we could easily have chosen any pair of black qubits to be in the same subgraph. So once we have this, we need to associate one of them with black trap qubits, one of them with the red trap qubits, and one of them with the actual computation we want to perform. So if we want a red trap qubit, we need it to be in a separable state, which means we need to measure its neighbors in the Z basis. Equally, if we want black trap qubits, we need them to be in a separable state, so we need to measure their neighbors in the Z basis. So we're preparing them as Z eigenstates. So what this means is that in the black trap subgraph, we're going to prepare all of the red qubits to be in Z eigenstates, and in the red trap graph, we're going to prepare all of the black qubits to be in Z eigenstates. So the result of this is just to leave separable trap qubits on both the black vertices and the red vertices, and to leave our computational graph separate. So on the computational resource state, I realize here it's only got 3 qubits shown, but we can make any, so if we did a much larger graph, the resource state we would have left for the computational graph would contain 1/3 of the black qubits. And it would have an intermediate red vertex between all of the qubits, so we can turn it into any graph state we want, simply by choosing whether these red qubits are Z eigenstates or whether we measure them in the Y basis instead to implement a control Z. So the idea is that we will implement our computation on this computational subgraph just using a standard measurement-based fault tolerance scheme. So there's probably the best known one is from Robert Reisendorf and others that uses a modification of the surface code to encode the computation. So we simply choose the parameters for that scheme on the computational subgraph such that it has distance 2s minus 1. So the reason we do this is that if we have s minus 1 errors, then you correct to a state that's sorry. So the point of this is basically so that when it corrects to a state, if the weight of the error is less than s minus 1, is less than s, then you get the correct output. And if it's greater than s, then maybe you do or maybe you don't. So the a sketch of the proof that this behaves as intended goes as follows. I'm not going to actually rigorously prove it because we have a paper up on the archive and it's about 40 pages long. So there's a lot of subtleties in the proof that need to be taken care of. But just an overview of how it works is basically we're going to, by doing the fault tolerant computation, we're imposing the criteria that errors of weight s-1 or less are corrected by the fault tolerant scheme. This means the resource state for the fault tolerant scheme is composed of black qubits only, because you choose the measurements on the red qubits simply to prepare the resource state necessary. So in the case of that RHG scheme I talked about, it's a regular three-dimensional lattice. It's not really a square lattice, but it is a regular lattice in 3 dimensions, which is fairly simple to parameterize and so on. So we simply choose the z measurements and the y measurements on those on the computational subgraph, such that we get the necessary resource state for their scheme. Then errors on the red qubits, so errors on the black qubits correspond to just errors on logical qubits in the RHG scheme directly. However, errors on the red qubits correspond to essentially errors in edge operations. So errors in the entangling operations in the scheme, which create errors on potentially 2 qubits instead of 1. So if you have an error on a red qubit, that translates into an error on 2 black qubits. So those qubits, those errors are counting for double. The other tricky thing about these red qubits is that their location as to which subgraph they wind up in is correlated. And that's slightly messy, but you can account for that, and you reach the conclusion that only an error of weight s over 5 or more can lead to an incorrect outcome. So if the weight of the error on our original resource state, so on our complete graph with the extra qubits added on each edge, then the weight needs to be at least s over 5. If it's less than that, the computation will just work. You'll get the correct outcome because the fault tolerant scheme will correct the error as it goes along. Okay, so the errors occur on individual trap qubits. Right? If a local poly error occurs on a trap qubit, it's not necessarily detected. So if we prepare a trap qubit, for example, in the plus state, so 0 plus 1 over root 2, then that's an eigenstate of x. So if we have a poly z error on it, it will definitely be detected. If we have a poly y error on that qubit, it will definitely be detected. But if we have a poly x error on that qubit, it won't be detected at all. So if we average over all possible choices of the trap qubits, so that's just one of 8 different settings in the xy plane, we come to the conclusion that the probability of detecting an error is at least a half. If the error is a z error, you always detect it if it happens on a trap qubit. But if it's an x or a y error, there's a 1 in 2 chance that you won't detect it simply because the state that qubit was prepared in isn't sensitive to that error. Just either because it's an eigenstate of it or it's close to an eigenstate of it. Okay, but when you take these together, so the total probability then of detecting a particular poly error on of detecting a poly error on a trap qubit is at least 1/6, which means the chance of Bob going undetected on a given trap qubit is 5 and 6, and we know he has to have at least at least S over 5 errors. So the probability of Bob cheating and going undetected is then 5 over 6 to the power of S over 5. Now, you may ask where the factor of 5 comes from here. It turns out it's due to the, it depends on the resource state you're creating. So in the RHG scheme, their particular resource state, it turns out that it's 4 edge colorable. And the number here that you have on the bottom, 5, is always equal to the edge colorability plus 1 of the resource state. So if you show me a similar fault tolerance scheme, but where now the graph is, say, 3 edge colorable, then this factor will drop to 4. Okay, so that's the last thing I'm going to say about the authentication, and I'll just finish up by saying a little about the experiments. So recently we've been lucky enough to convince some experimentalists in Vienna to implement the original scheme we discussed in a quantum optics setting. Now, there's only 4 photons involved, so we're not at the stage where we could have done any meaningful authentication. But we can do a computation that's completely blind. So this is a schematic of their setup, but basically you have 4 different photonic qubits coming out, and this thing generates a 4-qubit cluster state. So it's normally it's a linear cluster state. So you have the 4 qubits. The graph is just a straight line with the 4 qubits along it. So we can use this to demonstrate a bunch of building blocks of a larger scale blind computation. So so we can demonstrate single qubit rotations, Hadamard gates, for example, or 2-qubit gates. So we can do entangling gates as well. But basically, we're able to demonstrate all of the various segments of a brickwork state, of a larger scale brickwork state. So there's not really any part of it that hasn't been shown individually. Now, in our setup, obviously we wanted to use all of the possible settings. So we want to use, when we did a blind computation, we wanted to try it with each of the possible choices of input states. And obviously that increases exponentially with the number of qubits you add. So in this case, the number of qubits that are blind is only 2. So we're only preparing randomly chosen qubits for the second and third qubit of this graph state. The rest are prepared in known states. So the state of the first qubit and 4th qubit is fixed throughout. But basically, we demonstrate the various building blocks and a couple of algorithms. So on top is Grover's algorithm, and on the bottom is an implementation of the Deutsch-Josa algorithm. So it turns out that the guys in Vienna know their stuff, and we're able to get reasonable fidelities for the outcome of these. So particularly for the Deutsch-Josa case, we get fairly high probability of getting the correct outcome. But what I think is more interesting about the experiments is that we're able to show how much information is leaked, subject to certain assumptions about the environment. So in order to actually show how much information is leaked, we need some kind of model that says what constitutes leaking and so on. And we need to make some assumptions. So we need to assume that there's no side channels. For example, Bob might be able to hear Alice put in place her faceplate or something like this, which would tell him maybe what state she's prepared, or maybe he sees her do it, or something like this. We can't control for things like that. That's something we're going to assume that the endpoints of the computation are secure. But if we assume that, and that the only information that Bob can gain is the information Alice sends him in the form of the qubits, and the information she sends him in the form of the classical information, then we're able to bound the amount of information that's leaked simply using the Halevo bound. So the way we do this is we perform the experiment a whole load of times. We do tomography to determine. I keep saying we do the experiment. I didn't do the experiment at all. Stephanie Bars probably did almost all of it, and Philip Walter in Vienna. So basically, the idea is you perform the experiment many times, making different measurements at the end, and you use these measurement results to do tomography to determine what the initial state actually was, rather than what you think it is. And then we just plug it into the formula for the Halevo quantity, and that gives us a bound on the amount of information that's leaked. So in the case of a single qubit rotation, there's one of 8 possible rotations that could have been performed. And if you choose those uniformly randomly, you find that you would require 3 bits to describe it, to uniquely identify the rotation that was performed. However, when you calculate the Halevo quantity in this case, you find that it's only 0.17 bits. Now, if Bob has some prior information on the distribution of states Alice is going to send, they're not uniformly randomly chosen, for example, then this probability changes slightly because we have to maximize it over all possible distributions. But Bob never gains a substantial amount of information from the classical and quantum information that is sent from Alice to him. So if the blindness is compromised, it has to be compromised at Alice's side of the computation. Her device has to be insecure. Actually, what she's sending to Bob isn't revealing much information at all. So that's it. Thanks very much for listening. If you're interested in learning more, there's a couple of papers on this. There's our original paper from Fox in 2009. There's a recent paper myself and Elham have on the archive, which is proving the security, saying this verifiability authentication property in excruciating detail. And then there's the recent experiments with the guys in Vienna. So that's in Science, or again on the archive. So thanks very much for listening.
Okay, thank you very much, Joe, for this very nice talk. So I would first like to ask the viewers of the stream to ask their questions on the Q+ thread, or to join the Hangout, because we have currently one free space here, so you can also come in live and ask them. And I think we have a question from Yutaka, is that correct? So please, Yutaka, maybe start with your question.
Yeah, we have a question. I don't understand when is the artist knows that it's correct, is the successful is the quantum computation is. This is a very simple question.
I'm sorry, could you repeat the question? I didn't quite.
Yeah, right. Is I send the information, input to the Bob to the calculator to receive receive back to that artist receives the successful information, so the correct information after the calculation. I don't understand. Is the totally is the Alice and Bob is know that it's the information, Yeah, share the information. It's the bit is the correct. It's the measurement outcome. Or the bit is the outcome of the computation.
So
Then
you're asking
yeah.
how she knows that the outcome must be correct. Is that?
Yes, exactly.
Okay. So basically, sorry, I mean, maybe I did explain it badly, and it's quite hard to. I haven't realized how hard it is to give a talk when you can't you can't really see faces very clearly in front of you. So it's hard to tell when you're not explaining something well. And
right.
I didn't explain things very well at a number of points. But basically, what we do is we create these traps. The point of which is to determine whether or not Bob gave the correct result, the correct measurement result. Now, we can't test all of the qubits, but we can make the probability that Bob cheats and it's not detected by one of these traps exponentially small. And by doing this, we're ensuring that Bob must have followed the protocol. And so what we're using then is we're using the correctness property of the protocol, so that the protocol does actually implement the measurement-based computation you want to perform. So if you wrote down your circuit correctly, and Bob was not able to change that circuit, then the outcome of that circuit must be correct. The outcome of your computation must be correct, because Bob couldn't deviate from the circuit. Now, it's entirely possible for Bob to deviate and you to get the wrong outcome, but in this case, you know you get the wrong outcome, except with exponentially small probability.
I see. Just very smart, this idea. Yeah. Good. Danny, may I have a question? Another question?
I think Daniel's nodding.
Okay, right. It is possible to sort of extend this. Now it's a sort of bipartite. It's the Alice and Bob is sharing the idea, but the Alice and Bob and Charlie is sharing.
So so actually, this is I think one of the more promising directions. So it turns out that if you add in a second person, Charlie, there's lots of stuff you can do. I mean, you can do lots of things, but the most obvious thing to do, which we discuss in a few of the papers, is to do a setup where Bob and Charlie have quantum computers and Alice has no quantum power at all. So before, I had been assuming Alice could prepare individual qubits, but actually, if you have Bob and Charlie don't talk to each other, but they share entanglement, then Alice can instruct Charlie to make measurements on his qubits, on his half of entangled pairs, so that he projects the qubits Bob has into these XY plane states that are necessary to run the protocol. So it's entirely possible to run a completely blind protocol in this way with two remote servers, as long as they don't communicate. In which case, you totally remove the need for Alice to have any quantum power at all. You know, she doesn't need anything. I mean, she needs a pencil and a paper and a way to, pencil and paper and a way to communicate with both Charlie and Bob. But that's it.
Okay, so I also have a question. I'm trying to understand, I'm quite intrigued by this authentication part of your protocol, and I'm trying to understand if someone were knocking at my door now and trying to sell me a 100-qubit quantum computer, and he was, say he claims he has a fidelity of 95% or something like that, what with which probability could you authenticate it? I guess you are kind of using error correction and fault tolerance, so it might be hard for you to give me a number. But I mean, what's your feeling?
Okay, so I mean, there is stuff I can say about this. The paper we have on the archive at the moment doesn't deal with it doesn't deal with fault tolerance. It's proving that it's authenticated, and it's using fault tolerant techniques to do this, but it's not actually proving a fault tolerance threshold for the scheme. However, we know of ways to modify it that will allow this, but they're not in the paper. I guess we're thinking we might tack it on before we submit it, but maybe it will make it into another paper. I'm not sure. However, the problem of just plain fault tolerance, if you leave aside authentication, you just want to do a blind computation and you want to do it in the presence of environmental errors. So Tomoyuki has a really nice scheme on this, and so I think they have an error threshold of 0.43 or something %. So as long as your errors are below that threshold, just the fault they use the ORHG scheme as well. It's a slightly different configuration of qubits, but they just use our basic protocol with a different resource state, yeah, so they get 0.43%, which is pretty good. It's only about a factor of 2 off the actual threshold for that scheme. So it's not a huge overhead that's incurred. Now, in the authentication setting, it's going to be worse because there's going to be some redundant qubits that are introduced, which are entangled to your graph. The particular graph states we had there with the complete graphs, the number of them actually scales with the number of qubits in your computation, so that won't give a threshold straight off. You need to modify that. You need to take some ideas of that complete graph resource state and apply it to a regular graph, and certainly I can discuss how to do that if you want. But if you do that, then you get the same, you get a threshold again, essentially piggybacking on the fact that you're just using a fault tolerance scheme and you're only doing a constant increase in the error rate. However, the constant will be much bigger, so it will be like, I don't know exactly, but I'm going to guess about a factor of 10 worse than Tomoyuki's scheme.
Okay, thanks very much. There's a question from Tomoyuki who would like to know if the leakage of information in the experiment might come from the fact that sometimes more than 2 photons are emitted.
Well, not in this case, because we post-select on the correct number of photons. So this is a linear optics scheme, and linear optics quantum computing doesn't really have very good entangling gates. So you tend to post-select on the cases where your gates worked. And so this means that we're looking at only a subset of the statistics where we got exactly the right number of photons. Now, Elham has done some work, I guess. It's probably for her to talk about more on this, with where you don't necessarily get 1 qubit at a time. You get more than 1. In our case, however, I believe she's shown that you can still have security in that case. But if you in the experiments that were performed in Vienna, because we always have the correct number of qubits, actually the errors are coming from not preparing the correct state. So you assume that you're preparing one of 8 quantum states, and these quantum states are uniformly distributed around the equatorial plane of the Bloch sphere. So if you average over all of them, it yields the maximally mixed state. However, it turns out that in reality, experiments aren't perfect, and so you're not preparing exactly the state you thought you were. So the distribution of these is a bit different than what you think it is, which means the average isn't in exactly the same place. So it's possible to learn more from a single qubit than you would naively think by just looking at our theoretical protocol, if you're not preparing exactly the correct quantum states. So an example of this would be, so the idea is we showed blindness by averaging over this secret variable OR, and that mapped between two orthogonal quantum states, so that you get the maximally mixed state. Now, if you have any pair of states and you get an OR is unknown, then in our scheme you get the maximally mixed state. However, in practice you don't, because the two states you prepare are not completely orthogonal to each other. So it's possible to learn some amount of information because each pair will yield some other mixed state that's a little bit offset from the maximally mixed state. So you're potentially learning some small amount of information from that.
Okay, there's another question from Ravi. Before you ask it, Ravi, there's another one from Samkal. If you could suggest more literature on the subject, but please answer them together with Ravi's question, maybe.
It guides your choice of resource state in a particular measurement-based quantum computing protocol. I mean, because you mentioned something about brickworks. Instead of brickworks, you're using graph state, right? So I was just wondering.
Yeah. So these are all graph states. The only issue is choosing which family of graph states you want to use. So the original papers on this by Reisendorf and Briegel, and subsequently Reisendorf, Briegel, and Brown, use cluster states, which are just regular square lattices, right? But they initially, when we looked at this problem, we didn't realize that we could hide z-basis measurements. So for the cluster state graphs for those graph states to be universal, you need to make xy plane measurements and you need to make z-basis measurements. And we didn't know how to do the z-basis measurements. We didn't know it was possible. So we came up with a resource state that only required xy plane measurements. Now, there's nothing really special about it. We wanted to give a concrete protocol, so we just came up with a family of states that worked for xy plane measurements. However, if you know anything about measurement-based computation, you can probably sit down and within 10 minutes work out another family of states that will also work. It's possible that you can reduce the overhead. At the moment, we're using 10 qubits to implement a universal set of gates. So we're doing one, well, they overlap. So actually, you've got a factor of 8 to 1 in terms of the number of qubits you need per gate. But that's doing either local gates or entangling gates. So, I mean, if you think carefully about the family, you can probably reduce that by a factor of 4 or something. So it's probably, you know, you can probably reduce the overhead of our scheme a bit. But you won't be able to do it by more than a factor of 4 or so. Just due to the fact that it doesn't take that many qubits in our scheme to implement each gate, and you're never going to get it below 1, or well, below a pair of qubits for an entangling gate. Yeah, I mean, then subsequently we realized we could do z-basis measurements, and that's what led us to these other resource states. The reason, I mean, I find the new this resource state we have quite aesthetically pleasing, this one where you take the maximally connected graph and you put qubits in the middle of it. Simply because it's this is going to sound crazy, but it's kind of like a liquid or something. You can break off part of the state, and you just have a smaller copy of the same state. So if you take any subset of black qubits, black vertices in the graph, and you only keep qubits that the neighbors of which are all in that particular subset of black qubits, and the black qubits themselves, then you just wind up with a smaller one of those graphs. So you have the complete graph again on those with an intermediate qubit on each vertex. So this is quite nice in that you can break it up into any number of computations that don't interact with each other, that are all kind of identical, and there's no particular role of any one qubit. There's no special qubits. There's only 2 types of qubits in the whole thing, and they're all on equal footing. That's nice from a technical point of view when we want to prove the authentication, because we want to prove that we can detect errors on all the different qubits. And if we only have 2 types of qubits, then it's simpler. In a cluster state, for example, you'd have the XY position within the cluster state, and that potentially things could become trickier because how far into the computation you are might matter or something. So this seemed the simplest route to us to rigorously prove the authentication. But there's other things you can do.
Thanks.
Okay. Okay, if anyone else has a question, please raise your hand now. Okay, so in that case, I would say let's thank the speaker again.